John-Michael Colef doing problem 1 of homework 5. So, problem 1 wants us to go through a proof, sort of. So if we have random variable z is equal to random variable x plus random variable y, we can write f of z, so this is big F of z. Well, we know that that's probability of z random variable less than or equal to some z. Well, we know, because we're given, z random variable is just x random variable plus y random variable, so we can write this. And this is simply equal to f of x plus y, which is equal to this, where the region that we're integrating over is x plus y less than or equal to z. So we basically turned this into an integration of two random variables. So we can proceed in two ways. So the first way, we can solve for y and say that y is less than or equal to minus x plus z, and in that case z is just some constant over here, minus x is the slope, it goes down like this, and this is the area that we're concerned with. Another approach is to solve for x, so we get x is less than or equal to minus y plus z. So this is x, this is y. And we can draw a similar graph where this is y and this is x, and we have this region that we're concerned about. So now let's actually look at the integral. So I'm gonna do it for both conditions. So I'm gonna try to divide my page in nice half. So this half will do the first condition where we solved for y. So, and this I'll do later when we solve for x. All right. So here we have big F of z. Now we have our double integral. So now we got to be careful. So now we're looking at here when we solved for y. So we have to go first. The first integral is from curve to curve, but there is no other curve. So we're going from negative infinity, right, because we're only concerned with this area underneath this curve, to this curve. So we're going to go negative infinity to minus x plus z. And this is because we're going, the curve is a function of, this is y equals something. So we go from, we're going to integrate, when we integrate up like this, we're integrating with respect to y. So we have little x, y, xy, dy. And the second integral will be with respect to x, and we're going to go from negative infinity to infinity. So that's this integral. For the other one, for the other approach, it'll be similar, but it'll be opposite. So we're going, in this case, negative infinity to this curve, but this curve is going to be x equals something. So we're going to be integrating with respect to x. So it'll be negative infinity to negative y plus z, little f of xy, x comma y, dx, and then y goes from negative infinity to infinity. Now we want little f of z. Well, that is just a derivative of big F of z with respect to z. Now, the first integral that we do is the innermost integral, and we're going to get something from this integral that's a function of z. So we can actually switch integration and the differentiation with this first integral because we want to get at this guy first. So we have here this, and we can bring the derivative inside, d dz of, and now we have this guy. Right, I forgot to put my limits. Using there's a fundamental theorem of calculus, we just get the first integration. This just becomes f of xy, x comma at y equals a negative x plus z. So we get x comma z minus x. It's a sum, so. And we're left with this. And now I'm gonna, on the other side, I'm gonna do the same thing. So we know little f of z is equal to d big F of z dz. Same thing, same reasoning, because we're gonna consider this integration first. We can actually move the d dz inside. Here. And again, we're going to use the fundamental theorem of calculus to evaluate this. So here we get this. In this case, it's going to be at x equals z minus y, comma y, dy. Now, an interesting thing happens if x and y are independent. If they're independent, we can write this. Little f of x comma y is the same thing as little f of x times little f of y. So coming back to this integral, we have little f of z equals integral from negative infinity to infinity. This guy can be rewritten using this, if they're independent, as fx of x times fy of z minus x dx. Now this is the same thing as the convolution of fy of z convolved with fx of z. Similarly here, we'll have same reasoning. If x and y are independent, we can break them apart. So we get fx of z minus y times fy of y dy. Now this is just a definition of the convolution of fx of z convolved with fy of z. So this is a special case if x random variable, y random variable are independent. So now we have another method of doing the same thing. We can use the step function. So coming back to this guy, this integral, which is our original integral, which was big f of z equals this. Dx dy. X plus y plus to z. So we can write this because because x plus y must be less than z, we can, otherwise it doesn't exist, we can write this as we have the step function of z minus x plus y dx dy. Now, we can write this because we know that x plus y must be less than or equal to z. And the step function is 1 in this case for x plus y less than or equal to z. Otherwise, the step function is 0 and the integral is, it's 0. So that's why it shows we only care about the places where x plus y is less than z. And in this case, the limits are from negative infinity to infinity. Now, let's continue over here. So this stays the same. I'm going to distribute the minus sign inside the argument of the step function. So we have z minus x minus y dx dy. So now we can take one of two approaches. I'm going to do it both ways, but let's take the approach that we do this. So to put the parentheses around here. So what this is saying is that y cannot, so can't, be greater than z minus x. So y can't be greater than z minus x. Because if it is, this argument is negative and the step function is 0. Right? So in that case, our limits change. Right? Our limits are going to go, instead from negative infinity to infinity, it's going to go from negative infinity to z minus x. Because only in this interval is this step function equal to 1. If y, and by the way, and this is going to change the order of integration, because in this case we're only going to be integrating, with respect to y first and then with x, right? Because we're concerned with y. So I probably should have done another step, but I'll write it again. So y cannot be greater than z minus x, and that's why y is going to go from negative infinity to z minus x. Cannot go above that. That's one way of looking at it. And even in the other way of looking at it, it's the same thing. You'll get the same answer. So here we have, in this way, if we look at y, we're going to integrate with respect to y first, and then with respect to x. So if I rewrite this, I don't even need the step function anymore because I've changed the limits, and this is going to go to 1 in this interval. So I'm going to rewrite this. So we have f of z, negative infinity to infinity, negative infinity to z minus x, f of x y, x comma y, dy, dx. Now, if you look at this, it's exactly the same integral, right? So to find little f of z, you take the derivative of the inside, and you get the exact same answer at the end. Same answer. Now, we could have looked at big F of z like this. Instead of putting the parentheses around z minus x, we could have done z minus y minus x. I'm not going to put these first. I want to talk about this before I put. Actually, I could put these. Anyway, so what does this mean? This means that x can't be greater than z minus y. X must be less than or equal to z minus y. Otherwise, the step function will be 0. So we can write this. Since we're integrating with respect to x first, x has got to go from negative infinity to z minus y. It cannot go above that. And we're just left with this. If we go back, to when we solve for x in this case is the exact same integral, which we solve in the same way. To find little f of z, you take the derivative, and you do this whole business, and you end up with this. So for here, I'm just going to write here. We come to the sorry, this should be a z. We come to the same conclusion by the same work. I'm just going to write it. And then for this one, for this guy, we come to the same conclusion here. So either method, using the step function or using the step function, which was this method, or doing this method, it'll give you the same answer. Also, if you assume, in this case, in the step function method, the x and y are independent, you'll get the exact same thing because we have the exact same integral. So either way is a valid way of finding big F of z and little f of z. And that completes the problem.